The radius of K plus and F minus are 133 and 136 picometers respectively. What is the distance between K plus and F minus ions in potassium fluoride crystal? In ionic crystal, the cation and anion are touching each other. They are closely packed. So the internuclear distance between these two ions becomes the distance between these two ions. So here cation is smaller and anion is larger. They will be touching like this, and the radius of the cation and anion are given, and we have to find out internuclear distance. What is the radius of cation? Radius of cation is 133 picometers, and radius of anion is 136 picometers. So now what is the internuclear distance? This plus this, 133 plus 136. Okay, that is the internuclear distance, and that is nothing but the distance between ions. So what is the distance now? Distance is equal to 133 plus 136, that is equal to 269 picometers. So this is a very simple problem. Next problem. A metal crystallizes in a simple cubic unit cell of edge length 6.22 angstroms. What is the radius of metal atom? So that is the question, and we know in simple cubic unit cell there are 8 lattice points, and the atoms will be touching each other along the edge like this. So these are the two atoms touching each other along the edge like this. There are 6 more atoms. In total there will be 8 atoms present in the corners. 1 2 3 4 5 6 7 8. Okay, so here I have shown you only one edge along with which there are 2 atoms touching each other. So if you consider the distance as r here, okay, there is the radius of the other atom is also r. So if you consider this distance as a, that is edge length, there are 2 radii will be there. So what is the relation between the edge length and radius? That is equal to a is equal to 2r. So now what is given here? Edge length is given. Okay, so that is nothing but 6.22 angstroms, and radius we have to find out. So that is equal to 2r. Now r is equal to 6.22 divided by 2. Okay, so that is equal to 3.11 angstroms. Right. So this is a very simple problem. Okay, so along the edge there are 2 r. So 1 r is equal to what? Half of the edge length, a by 2. Okay, so that is why the radius of the atom is 3.11 angstroms. Right. Next problem. What is the packing efficiency in a face-centered cubic unit cell? We know there are 8 atoms in the corner and 6 atoms in the faces in face-centered cubic. Okay, so let us calculate effective number of atoms. Number of atoms in the corners into contribution of atom in the corner is 1 by 8. Okay, so that is 8 into 1 by 8 equal to 1, and 6 atoms are there in the faces, and contribution to 1 unit cell is 1 by 2. So 6 into 1 by 2 is equal to 3. So what is the total number of atoms present in 1 unit cell of face centered cubic? That is equal to 4. Okay, so effective number of atoms is equal to 4. Right, now how do we calculate packing efficiency? Packing efficiency is equal to volume of the spheres by volume of the unit cell into 100. Right, effective number of atoms is Z into volume of each sphere, that is 4 by 3 pi r cube. Okay, so this term will give the volume of all the atoms together present in the unit cell, and this is the volume of the unit cell, that is a power 3. Right, now packing efficiency is equal to Z is equal to 4 into 4 by 3 pi r cube divided by a cube. So edge length should be expressed in terms of radius of atom. Okay, how are radius and edge length related? 4r is equal to root 2a for face centered cubic. Radius and edge length are related as 4r is equal to root 2a. Okay, now a is equal to 4 by root 2 into r. Okay, so edge length 4 by root 2 into r whole cube, right, that gives volume into 100. If you simplify and calculate, you will get packing efficiency as 74%. That is the packing efficiency of face centered cubic. Next problem, what is the percentage void space in body centered unit cell? In a body centered unit cell, there are 9 lattice points, 8 at the corners and 1 at the center of the body. Right, so in total 9 lattice points are there. What is the effective number of atoms? As I told you, 8 atoms are in the corners, so effective number of atoms will be 1 and 1 at the body. So body centered position contributes as a whole to unit cell. So contribution is 1, right? 1 into 1 will be equal to 1. So effective number of atoms is equal to 2. Now what is the relationship between edge length and radius of the atom? And again here 4r is equal to root 3a. This is the relationship between edge length and radius of the atom. This we have to remember, right? Now what is the packing efficiency? Packing efficiency is equal to volume occupied by the atoms by volume of the unit cell into 100, right? So volume of atoms is equal to effective number of atoms into volume of each sphere, that is 4 by 3 pi r cube. Okay, so this is volume of sphere, this is number of spheres or number of atoms, right? This gives total volume of all the atoms divided by volume of the unit cell, that is equal to a cube, right? Volume of the unit cell is V, that is equal to length cube, edge length cube. Okay, so that is equal to volume into 100, right? Now what is the effective number of atoms? That is equal to 2 into 4 by 3 pi r cube divided by a. A is what? A is equal to 4 by root 3 r into 100, right? Okay, so this is a cube. Now simplify this, and if you calculate, you will get 68%, right? So what is packing efficiency? That is equal to 68%. Okay, now here it is asked void space. Okay, so packed space is 68%. So void space is what? Void space is equal to 100 minus 68, that is equal to 32%. Next problem. Copper crystallizes in a face-centered cubic lattice. The length of unit cell is 3.63 angstroms. What is the radius of copper atom? Here again the relationship between edge length and radius of the atom, and how are the radius and edge length related in face-centered cubic? In face-centered cubic, the atoms are present in the corners and on the faces. The atoms in the corners will not be touching each other, but whereas the atoms in the corner will be touching atom that is present on the face. So along with the face diagonal, there are 4 radii. Okay, so 4r is equal to root 2a. Okay, that is the formula you have to remember. So you have to find out now the radius of the atom. Okay, so 4r is equal to root 2a, right? So that is the formula we are using here, right? So now r is equal to root 2 by 4a, and now substitute the edge length that is given here, that is 3.63 angstroms, right? Now r is equal to root 2 by 4 into 3.63 angstroms. Now simplify this. So 4 will be cancelled, 0.975 times here. So root 2 is equal to 1.414. Okay, now multiply, you will get the answer as 1.28 angstroms, right? So after calculation you will get this answer. Now we'll move to the next problem. The radius of atom of an element is 80 picometers. If it crystallizes as BCC lattice, what is the edge length? Okay, here the problem is similar to the previous one, but here it is crystallizing in BCC. In earlier problem it is in FCC, right? Again the relationship between radius and edge length. So radius is given, we have to find out edge length. Our radius and edge length related in body centered cubic, they are related as 4r is equal to root 3a. Okay, so here radius is given and edge length we have to find out. Okay, so a is equal to 4r by root 3, right? This is the formula. Now substitute 4 into radius is 80 picometers divided by 1.73. Now if you simplify this and calculate, you will get the answer is 185 picometers, approximately 185 picometers. So that is the edge length of BCC that is formed by the element. Next problem. Cesium chloride crystallizes in body centered cubic. If A is its edge length, then distance between the oppositely charged ions is. We know in body centered cubic the radius is related to edge length as 4r is equal to root 3a. Okay, this is the formula that is applicable to BCC that is formed by the metal, but here it is ionic compound, right? This is applicable for a metal when identical atoms are present in the lattice, but here oppositely charged ions are present, right? So we have to modify the formula as per the ionic compound. So this is the structure of cesium chloride. Each cesium ion is surrounded by 8 chloride ions, and each chloride ion is surrounded by 8 cesium ions, right? So this is anion, or you can take it as cation surrounded by anions, right? So if you consider the body diagonal, okay, this is body diagonal and how many radii will be there? Okay, there are 4 radii. This is one radius, this is one radius, and 2 radii of this ion will be involved. Okay, so let us consider this as cation, right? So these are anions. So how many radii will be there? 4 radii will be there. Radii of 2 radii of cation and 2 radii of anion. Now this formula can be modified. This is written for the single metal, right? So this formula is applicable when lattice is formed by a single element, but here it is formed by 2 different elements. Or for ionic compound, you can modify like this. 4R is equal to what? Radii of 2 radii of anions, 2 radii of cations. So you can write it as 2RC plus 2RA. 2RC plus 2RA is equal to body diagonal length, that is not going to be changed, that is equal to root 3A, right? Now how can you write this formula? 2 into RC plus RA is equal to root 3A, or RC plus RA is equal to root 3 by 2A. Okay, so radius of cation. So in place of radius of cation, you can take radius of cesium ion, and in place of radius of anion, you can take chloride ion. RCS plus RCl minus is equal to root 3 by 2A. Radius of cation plus radius of anion becomes the distance between the two ions. Okay, radius of cation, radius of anion becomes the distance between the ions, or internuclear distance. RC plus RA is equal to this distance, that is nothing but the internuclear distance or distance between oppositely charged ions. So RCS plus RCl minus is equal to root 3 by 2A, right? This is the answer. Next problem, first 3 nearest neighbor distance for primitive cubic unit cell is. Primitive cubic unit cell is a simple cubic unit cell, and the structure is like this, and here eight lattice points will be there, and the atoms are present in the corners like this. Now what is the question? First 3 nearest neighbor distances. Nearest neighbors are what? These are the nearest, and these are the first nearest neighbors. And what are the second nearest neighbors? These are the second nearest neighbors. They are along with the face diagonal. Okay. If the corner atoms are the first neighbors which are present along the edge, the second neighbors will be along with the face diagonal. They are the again corner atoms, but they are present along the face diagonal, right? And third nearest neighbors will be in the body diagonal, right? So these two atoms are the next nearest neighbors. First nearest neighbors are along with the edge. The second nearest neighbors are along with the face diagonal, and third nearest neighbors are along with the body diagonal. So we have to find out the edge length, face diagonal length, and body diagonal length. Okay, so that is the answer. So what is the edge length? Edge length is A. Okay, so edge length is A. Now what is the face diagonal length? And if you consider this as the face diagonal length, right? So let us take triangle ABC, right? So as per Pythagoras theorem, AC square is equal to AB square plus BC square. So what is AB? AB is this length, that is nothing but edge length, that is equal to A, and BC. BC is again equal to A. So AC square is equal to A square plus A square, that is equal to 2A square. Or let us say the length of the face diagonal as B, then B square is equal to 2A square, or B is equal to root 2A, right? So the next nearest neighbors will be at a distance of root 2A. Okay, that is nothing but face diagonal length, and the next nearest neighbors will be along with the body diagonal. Okay, so let us consider this point as D, right? This becomes body diagonal length, right? So let us say the body diagonal length as C, right? So again this ADC, okay, ADC is a right angle triangle, so that is why the body diagonal length AD square is equal to what? AC square plus CD square, right? So in right angle ADC, AD square is equal to CD square plus AC square, right? So what is AC? AC is nothing but B. Okay, CD is again equal to the edge length. Okay, so that is equal to A square, right? So B square is equal to what? 2A square. So 2A square B square is equal to 2A square plus CD square, that is equal to A square. So that is again equal to 3A square, or AD square is equal to C square. AD is equal to C, or AD square is equal to C square. Okay, C square is equal to 3A square. Therefore C is equal to root 3A, right? So C is the body diagonal length. The next nearest neighbors or third nearest neighbors will be in the corners, and the length is equal to body diagonal length. Okay, so that is equal to C, or root 3A. Now what is the answer? The first nearest neighbors are at a distance of A, second nearest neighbors are at a distance of root 2A, and the third nearest neighbors are at a distance of root 3A, right? This is the answer. Next problem, first three nearest neighbor distance for BCC unit cell are. In earlier problem, we learned the nearest neighbor distance in simple cubic unit cell, but here it is asked for BCC, and we know the structure of BCC. It is like this. This is a body-centered cubic structure, and here one atom is at the center, 8 atoms are there in the corners, and the first nearest neighbors are along with body diagonal length, right? So these two are the nearest neighbors. Okay, or these two are the nearest neighbors. So this distance we have to calculate. These are first nearest neighbors, and the second nearest neighbors are present along with the edge. Okay, so that means we have to find the edge length. So that becomes the distance between second nearest neighbors and third nearest neighbors are along with the face, right? Along with the face means actually they are at the corners, and we have to calculate this distance. Okay, so that is nothing but face diagonal length. Okay, so these are first neighbors along with the body diagonal, and the second nearest neighbors are along with the edge, and third nearest neighbors are present in the corners, and the distance between the two atoms at the corners along the face diagonal, that becomes the distance between third nearest neighbors. Body diagonal length is equal to 4r, radii of 4 atoms, or 4 radii of atoms will be there. 3 atoms are there and 4 radii will be there along with this body diagonal length. So 4r is equal to root 3a. Now what is the distance between these two atoms? This is the total distance in which 4 radii will be there, and the distance between these two atoms will be half of it. Okay, half of this distance becomes the distance between two atoms. Okay, so the distance between the two atoms is given by root 3a by 2. Okay, so this is the distance between first nearest atoms. The second nearest atoms are present in the corners like this. The edge length becomes the distance between these two. So what is the edge length? Edge length is equal to a, right? So it is nothing but the distance between second neighbors, and the third nearest neighbors will be present in the corners again, and the distance is the face diagonal length, and face diagonal length is equal to what? Face diagonal length is equal to root 2a, right? So if it is a, this is a, right? So let us take body diagonal face diagonal length as b. Okay, b square is equal to a square plus a square, a square plus a square, that is equal to 2a square, or b is equal to root 2a, right? So it is the distance between third nearest neighbors, right? So now what is the answer? First nearest neighbors are present at a distance of root 3 by 2a. Second nearest neighbors are present at a distance of a, and third nearest neighbors are present at a distance of root 2a. Next problem, a compound formed by elements xy crystallizes in a cubic structure in which x atoms are at the corners and y atoms are at the center of the faces. What is the formula of the compound? Okay, so x and y are crystallizing in a cubic structure, that is nothing but a face-centered cubic, in which x atoms are present at the corners and y atoms are present at the center of the faces, right? X atoms are present at the corners. So how many corners are there? 8 corners, and contribution of atom that is present in the corner to one unit cell is 1 by 8. So what is the total contribution now? It is equal to 1. And y atoms, they are present at the center of the faces. How many faces are there? 6 faces, and contribution to one unit cell by the face centered atom is 1 by 2. So this is the total contribution. Okay, so how many atoms of x are there now? 1 and y atoms are 3. Okay, so what is the formula? XY3, right? This is the formula, and this is a very simple problem. Next problem, a solid has a structure in which W atoms are located at the corners of the cubic lattice, oxygen atoms at the center of the edges, and a sodium atom at the center of the cube. The formula of the compound is, so what are the atoms present here? Sodium, tungsten and oxygen. Okay, sodium is present at the body centered position, right? Atom at the center of the cube means it is present at the body centered position. So what is its contribution? Its contribution is 1. And oxygen atoms are present at the center of the edges, right? Oxygen atoms are present at the center of the edges, whereas tungsten atoms are located at the corners of the cube. Tungsten atoms are present at the corners. So what is the contribution? 1 by 8, and 8 corners are there. Number of lattice points into contribution of each lattice point to unit cell will give total contribution. So that is equal to 1. And now for oxygen, where are they present? They are present at the edges. And as there are 12 edges, and contribution of each edge lattice point to one unit cell is 1 by 4. 12 into 1 by 4 is equal to 3, right? Now how many atoms of sodium are there? 1 sodium atom, 1 tungsten atom, and 3 oxygen atoms are there. So what is the formula? NaWO3, right? So this is the formula of the compound. Next problem, how many unit cells are present in 5 grams of crystal AB having a rock salt type of structure? And here the formula mass of AB is given, that is 40, right? This is formula mass, and we have to find out a number of unit cells. Before finding out number of unit cells, we'll find out a number of moles present in 5 grams of the crystal, right? So what is molar mass? 40, right? Now number of moles is equal to mass by molar mass. So given mass is 5 grams and molar mass is 40 gram per mole. Okay, so that is molar mass. So how many moles are there? 1 by 8. Okay, so these are the number of moles. And now we know 1 mole contains Avogadro number of ionic pairs. Okay, because this is ionic compound having the formula AB, right? So 1 mole of compound contains Avogadro number of ionic pairs, right? So 1 mole contains Na. This is Avogadro number of pairs of AB. Okay, so how many moles are there? 1 by 8 moles are there. So how many pairs are there? Okay, now number of pairs present in 1 by 8 moles will be equal to, for 1 mole these many. For 1 by 8 moles, it is 1 by 8 into Na pairs. Okay, so these are the number of pairs in 1 by 8 moles of number of pairs in 1 by 8 moles is 1 by 8 into Na pairs. Okay, that is present in 1 by 8 mole of the crystal. Now what is the question? We have to find out number of unit cells. Okay, this is a rock salt type of structure. Okay, that means it is similar to sodium chloride. We know the structure of sodium chloride, in which sodium is present at the center and at the edges, right? Whereas chloride ions, they are present on the faces and corners. Okay, so similarly here A atoms or A ions, they are present at the body centered position and at the edges, right? And B ions, they are present at the center of the faces and at the corners. So what is the effective number of A? Effective number of atoms of A is 4 and effective number of atoms of B is also equal to 4. So how many pairs are there? 4 pairs. So per unit cell 4 pairs are there. Okay. So now 4 pairs is equal to 1 unit cell. And we know the number of pairs in 1 by 8 moles or 5 grams of the crystal. So that is equal to Na by 8. Okay. Now Na by 8 pairs will be equal to how many unit cells? So number of unit cells now will be equal to what? 1 by 4 into this, right? 1 by 4, okay, into Na by 8. Okay, so that is equal to Na by 32, right? Okay, so these many unit cells will be present in 5 grams of AB crystal having molar mass 40 grams. Next problem, potassium crystallizes in a body-centered cubic unit cell. The mass of one unit cell is body-centered cubic. Means the atoms are present in the corners and at the center of the body. So how many atoms are there in total? If you calculate the effective number of atoms, it comes out to be 2. Okay, 8 at the corners and the contribution is 1 by 8 and 1 at the body centered position. So the contribution will be equal to 1. 1 into 1 is equal to 1 and here it is equal to 1. So what is the effective number of atoms? Effective number of atoms is equal to 2. Now 2 atoms make 1 unit cell, right? 2 atoms make 1 unit cell and the mass of 1 unit cell we have to find out. So we have to find out the mass of 2 atoms, right? So what is the mass of 1 mole of potassium atoms? 1 mole or Avogadro number of atoms has mass equal to 39 gram, right? So this is nothing but molar mass of potassium. 1 mole of potassium has mass 39 gram or Avogadro number of atoms will be having the mass 39 gram. So 2 atoms, that is nothing but the mass of 1 unit cell. 1 unit cell contains 2 atoms. Mass of 1 unit cell or mass of 2 atoms we have to calculate. 2 atoms have the mass equal to this by this into 2, right? So 39 into 2 divided by Avogadro number of atoms. Okay, so this is mass of 2 atoms or 1 unit cell because 1 unit cell contains 2 atoms, right? So that is equal to 78 by Avogadro number of atoms is approximately, I am taking it as 6 into 10 to the power of 23, right? So this will cancel 12.95 and this is equal to 10 to the power of minus 23 gram, right? Or that is equal to 1.295 into 10 to the power of minus 22 gram, right? This is the mass of 1 unit cell of potassium. Next problem, a metal is crystallized in FCC. The number of unit cells in it having 2.4 into 10 to the power of 24 atoms is. So it is a very simple problem. The metal is crystallized in FCC. So what is the effective number of atoms in FCC? Effective number of atoms in FCC is 4. Okay, because atoms are present in the corners and 6 faces. Okay, so effective number of atoms is 4. So 4 atoms is equal to 1 unit cell. 4 atoms is equal to 1 unit cell, and here we have to calculate the number of unit cells having these many atoms, right? 2.4 into 10 to the power of 24 atoms now contain how many unit cells? That is equal to this into this divided by 4, right? 2.4 into 10 to the power of 24, okay, atoms into 1 unit cell divided by 4. Okay, so that is equal to 6 into 10 to the power of 23. 6 into 10 to the power of 23 unit cells are there in 2.4 into 10 to the power of 24 atoms. Next question, in an atomic BCC, what fraction of edge is not covered by atoms? And this is the body-centered cube in which 8 atoms are present at the corners and 1 at the center of the body, right? Okay, if you see this, 2 atoms are present at the corner along with this edge. Okay, so that means if you take the edge, there are 2 radii coming into the edge, and these 2 atoms are not touching each other. Okay, so let us consider the edge as A, right? The covered portion is 2R, right? So covered portion along with the edge is 2R, and uncovered portion is equal to A minus 2R, right? So this is edge length, and covered portion is 2R, uncovered portion is A minus 2R. Okay, so this is the relationship between the radius and edge length. Okay, now 2R is equal to what? Root 3A by 2. Okay, 4R is equal to root 3A, or 2R is equal to root 3A by 2. Now substitute 2R here. So uncovered portion now becomes A minus root 3A by 2. Okay, so this is uncovered portion, and what is the fraction now? Fraction will be equal to uncovered portion divided by the total length. Okay, so this is uncovered length, and length is A. Now if you simplify this, you will get the answer as 0.134. That is the fraction of edges uncovered by the atoms.